Hello, everyone. Thank you for joining us for today's webinar. My name is Wade Sisson, and I'm a member of the team here at Advanced Clustering Technologies. It is our pleasure today to host this live event with our friends at Cornelis Networks. We partnered with Cornelis last fall to promote their Omni-Path Express networking fabric, which is now able to be integrated into our HPC solutions. And they are here today to give you an inside look at Omni-Path Express and what it can do for you. Without further ado, I would like to introduce you to Brandon Singer from Cornelis Networks.
Thanks, Wade, and I will share my screen. First, we have Russ Fromkin, who is the VP of the Worldwide and Channel Sales, and Glenn Brook, who is our Senior Solution Architect. Okay, so now I'll get into it. Here's our notices and disclaimers, and we'll go into what you'll be hearing today. We'll start with an overview of Cornelis Networks, a brief background on the company. Then we'll go into our product portfolio and positioning. Next, we'll talk about the success with Cornelis and conclude with the contacts and questions. So here's a brief timeline of Cornelis Networks and how we got to where we are today. Started with Silverstorm Technologies, which was founded in 2000. Pascal was then founded in 2001, and both of those companies were acquired by QLogic in 2006. Then in 2009, the InfiniBand product line was launched. In 2012, Intel acquired QLogic HPC as well as the Cray ASIC team, and in 2016, launched the Omni-Path brand. In 2020, Cornelis Networks was founded, where we acquired the Intel Omni-Path business, and we support over 500 existing Omni-Path users today. Here you can see some of the places that Omni-Path is deployed. We have over 500 deployments, and we are in 42 of the top 500 supercomputers. Some of the deployment industries that we're in are the national labs, HPC cloud, oil and gas, the automobile industry, artificial intelligence, and some of the traditional HPC areas such as universities, government research labs. Here's a brief quote from Addison Snell, the CEO of Intersect 360. It reads, "A few years ago, InfiniBand was the de facto open standard for scalable, low latency systems. Cornelis' investment in Omni-Path combined with the NVIDIA acquisition of Mellanox suddenly flips the conversation. Now it is InfiniBand that can potentially be viewed as proprietary to a single processor vendor, whereas Omni-Path Express is an open multi-vendor solution. Omni-Path has been optimized for high-performance computing, high-performance data analytics, and artificial intelligence. This is due to our scalability, our low scalable latency, extreme message rate, and our highly scalable bandwidth." Next, I'll pass it over to Glenn to talk about our portfolio and position.
Thank you, Brandon. So I'd like to start today by talking to you about our current product line, Omni-Path. It's a 100 gigabit solution. And then we'll move forward a little bit more, talk about a software release, Omni-Path Express, that is due out in the next few months, and then wrap up with a little bit of discussion about Omni-Path 400, which is due out in early 23. Our current solution with Omni-Path offers an end-to-end, one-stop shop for a leading network and fabric on any sort of supercomputer or cluster that you're interested in deploying. We have industry-leading performance and the lowest total cost of ownership. It makes for an extremely strong value argument. What we have in the portfolio, we have a complete set of host and management software. It's really liked by most of the administrators that have to deploy such clusters. Standard sort of PCIe adapters, edge switches, director class switches, cables, and a new gateway product that we launched last year that allows you to tie Omni-Path interconnects into InfiniBand and Ethernet networks as necessary to support things like storage and external access and things like that. I'd like to give you a little bit of detail at the technical level about some of the key differentiators between Omni-Path and InfiniBand. You saw earlier that we clearly have our roots out of InfiniBand and inherit a lot of that capability. But we've extended that, in particular with a lot of the intellectual property that came from Cray and the Aries interconnect. So first and foremost, and probably one of the most defining characteristics in terms of the difference, is the fact that Omni-Path is built around flits. Okay, so InfiniBand, you end up with messages, and those messages are then transmitted, and they run 256 bytes up to 4 kilobytes, whatever your maximum transfer unit size is set to. Well, Omni-Path takes those MTUs. We also accept larger MTUs, 8K and 10K, but then we immediately tear them down into flow control digits, flits. Each flit is 65 bits, and they form a giant pool of available pieces of data that need to be communicated on the network. And then the ASIC then collects from that pool, depending on priority and different needs for traffic management and routing, and assembles link transfer packets. And those link transfer packets are 16 flits put together with a CRC. And this is an important differentiator, because it means that all of the traffic on our network is uniform in size, and we're able to fully optimize the network for communicating with those size link transfer packets. Now, the other advantage of using flits is that while we have these same size packets, we have a much finer grained control over the actual data and payload that's included in each link transfer packet. So it's possible for us to deliver much higher levels of resiliency and performance and consistent traffic movement and behavior, especially under load, than would be if you were working at the typical MTU level. One example of what we can do with having these flits is the traffic flow optimization. And essentially it amounts to being able to preempt certain types of traffic with higher priority traffic. And this is an example of doing that. So on the left, you have some storage traffic coming in, and at the top, and then below that, you have a link transfer packet that's got MPI traffic. And within that MPI packet, you've got some really high priority traffic, and that's probably something like a synchronization or maybe a small collective. And then you've got some more traditional communication data that needs to go across. And so it's a little bit lower priority. Well, you'll see what happens is, as it comes into the ASIC, each one of these packets is torn back down into their constituent flits, and then immediately they start rebuilding these link transfer packets for egress. And so you see that the storage packet starts going out first, but as soon as it gets some of these higher priority MPI data flits in place, it immediately preempts everything else, moves them to the header line, and includes them in that first packet. Okay, and so this is really important. This is actually what allows us to deliver much more stable performance even under heavy load, and provide for scalability on much larger machines and deployments. Another advantage of working with the link transfer packets is the way we're able to enforce packet integrity protection. So essentially what happens is each link transfer packet has its own CRC, and when it's sent, it's held in the send buffer until the receiver is able to check that CRC and verify that it's okay. If it's okay, the packet is then torn down into its flits, pushed into the pool, and they're available for further egress to another site. If it's not, we immediately trigger a resend from the send buffer. And so essentially what you end up with is no additional latency at all for the air checking, because it's actually built into the transport at the fabric level. And that's very different than, say, forward error correction, where you have to include additional payload on each of the messages to be able to implement the algorithms. One difference that's not noted explicitly on here, but I'll speak about very briefly as well, deals with the interswitch links. With Omni-Path, we're able to down each of the 4 lanes in an interswitch link independently. And because of that, we're able to maintain the link throughout an MPI job, even if it means degrading the performance slightly to do so. That's often advantageous if you have particularly large jobs running on large resources, where it could cost thousands or tens of thousands of dollars when you lose that running job. So in this case, we're able to monitor each of those lanes independently in the link and down them and notify administrators, right? So once they're aware that there's a link that's starting to suffer some lane degradation, they'll be able to drain nodes and replace that without ever having to bring the cluster down as a whole, or interrupt any of the network traffic. So that's one way that we're also able to add a whole lot of resiliency to the overall network. So now that you know a little bit more about some of the technical differentiators, I'd like to talk to you about how we kind of tailor our current solutions by the application space that you're working in. Okay, we loosely break these down into the three areas that were mentioned earlier for optimization with Omni-Path: high performance computing, high performance data analytics, and artificial intelligence and machine learning. And in general, what you see here is a growing dependence on bandwidth as you move through that stack. So to start with high performance computing applications, these are typically modeling and simulation type things in aerospace, automotive, oil and gas, drug discovery. It's the sort of thing that folks have been doing on HPC systems for decades at this point. These sorts of applications tend to be very highly optimized, and they tend to be much more sensitive to latency and message rates than bandwidth. In many cases, in fact, in most cases, they do not saturate 100 gigabit links. And so we're able to deploy single rail Omni-Path Express solutions and provide leadership class performance, excellent performance at incredibly good prices. Okay, so that's one of the really strong areas for Omni-Path, is that traditional high performance computing environment. Moving forward to high performance data analytics, we start to look at things like graph analytics, statistical data analysis, and you begin to see more of a dependence on streaming data in, getting data movement. And that increases the dependence on bandwidth, but most of the algorithms, particularly in graph analytics and certain types of statistical analysis, still do a lot of tightly coupled compute across nodes and have to communicate a lot. And in fact, in many cases, they do so with small messages. And that means that they're still very sensitive to latency and message rate, although it typically does occur in phases with the I/O, being the bandwidth portion later on. And in these sorts of environments, what we are seeing as being the best solution is a dual rail Omni-Path Express deployment. It does a really good job of balancing the compute and the communication needs, as well as providing twice the message rate, and certainly leadership class in our performance in the 200 gigabit environment. Okay. And finally, as we move to artificial intelligence and machine learning, you end up in a situation typically where you've got very, very dense nodes, often with a large number of GPUs, and it requires a significant amount of bandwidth to keep all of those GPUs fed, right? So in this case, we actually deploy even more rails in many cases. So dual rail is a good starting point, particularly if you only have 1 or 2 GPUs. But if you start to build up to 4 or 8 GPUs, quad rail deployments offer a very, very cost-effective solution for exceptional performance. And most importantly, you can scale your need for bandwidth at the node in increments of 100 gigabits as you increase your compute by adding additional GPUs. So these are kind of the general approaches we take when we're trying to tailor the Omni-Path solution to the various application environments. Moving forward, I'd like to talk to you a little bit about Omni-Path Express, which is essentially an entirely new software stack that is being deployed this quarter. And it will offer extended performance, increased performance for existing Omni-Path customers, and it'll serve as the foundation for all of the development moving forward on the Omni-Path software side, including into Omni-Path 400, which is due out in 23. So fundamentally, the Omni-Path Express software stack is built around a new OFI libfabric provider. Okay, it's native and it's built directly on top of the hardware driver. This is really fundamentally a complete reworking of a provider. It goes all the way back down to the bare metal driver and works up. Regression controls have been in place to ensure that every feature that is implemented within the OFI libfabric interface is done so at absolute minimal cost and overhead. And the end result is that we've gotten incredibly good performance improvements, and also been able to extend our support for a much broader variety of applications and interfaces and APIs out in the open source community that leverage that OFI libfabric interface. Okay, so this is a little bit different than in the past. where we were using PSM2, and each one of these interfaces that for different application stack or different API would oftentimes require a little bit of tuning or retooling in the PSM2 layer. By moving to this OFI libfabric interface as being the interface into the networking system, it allows us to focus on ensuring that each of the modules within that interface is as optimized as possible, and thus be able to provide optimized performance to that much broader array of application space above it. Okay. It also is worth noting that the libfabric provider sits alongside PSM2 and the verbs provider in the Omni-Path stack. So all of the features that you're accustomed to with existing Omni-Path deployments, they will all still be there. They'll all still be moving forward. And you will be able to transition from the existing PSM2 software stack and the use of that provider over into the use of this new libfabric provider, even on a job-by-job level if you want to. So it's a smooth migration path, and it offers a significant performance increase, and customers will be able to move into that at the rate that it matches their need. I mentioned that we saw some good performance improvements with the new libfabric interface, and now I want to walk you through a few of them. These are some of the early performance numbers that we've gotten on, in this particular case, an Ice Lake with 36 cores at 2.4 gigahertz. We're seeing up to 18% latency reduction on the Intel MPI benchmark ping pong test. And message rates are over 2 times higher than they were with the PSM2 stack in the previous software release. And very importantly, we're also able to take those enhanced message rates and scale them all the way up to the entire node count, right? So this is 64 processes per node. That's a full node, and we've been able to scale that message rate all the way up, and ultimately reach over 500 million messages a second out of the node. One other thing of note is, if you look at the scaling chart there, we're able to actually provide roughly the same message rate and performance of PSM2 at half the number of processes. Okay, so that means the OPX, the Omni-Path Express provider, at 32 processes per node is able to perform very similarly to what PSM2 had been able to at 64. Okay, that's important in hybrid applications where you may not run quite as many MPI ranks per node, and instead use threading within some ranks. You're still able to drive the performance out of the network using a smaller number of processes. Now we want to move over and look at performance on an AMD Milan. These are 64 core chips at 2 gigahertz. You see very similar kinds of curves. The shapes are very, very similar. Slightly better improvement in latency. Part of that is because the stack was less tuned to AMD when we started, and so there's a little bit more low-hanging fruit to pick. We continue to tune with both Intel and AMD, and so we expect these numbers to continue to improve. Message rate, once again, is over twice what it was for PSM2, and it scales, in this case, all the way up to 64 processes per node, and actually even beyond that to 128 processes per node, which we don't have a bar on the chart, but you can see we got over 525 million messages a second at that level. And finally, I'd like to talk about where we sit with regards to HDR 100 and 200 at the moment. This is testing done on AMD Milan. And in looking at latency, what you find is that PSM2 is running about 10% behind HDR 100. And until you get to a large enough message size, in which case it cuts under and actually outperforms HDR. For the smallest message sizes, it's not at all surprising. The signaling rate on 100 is faster. So they have a physical advantage there. But what you see is, as soon as we move to the new Omni-Path Express stack, which is that red line, we not only surpass the HDR 100, we match the HDR 200 performance. And as we scale up, we scale significantly better. Okay, this is very significant because we've essentially just overcome the performance differentiator of an entire generation of physical hardware development, and done that by streamlining and optimizing the software stack. This software stack is going to be the basis as we move forward into the Omni-Path 400 product. And at that point, we'll be at parity with the competition at 400 gigabits of bandwidth, and the signaling rates will be the same. So their physical advantage will be gone, and it will make the software improvements that we've made today that much more impactful on the future generation of Omni-Path and its performance relative to its competition. And finally, I'd like to call your attention to the messaging rate over here on the right. You'll see that we get up to almost 2x the performance of HDR 200 at message rate per core. Now, I'd like to take a couple of minutes and briefly talk to you about Omni-Path 400, which is the next generation product coming out, and give you a little bit of detail about it. It will be built around a PCIe Gen 5 foundational card, and we will offer high density switches and directors, much the same that we do here. The fabric itself will be 400 gigabits native, and you'll be able to bifurcate it to 200. So you'll be able to double the port count with splitter cables if you need to. Now, what I'd really like to do here is just kind of give you a general overview of what's going to be different about the next generation of Omni-Path. What are the guiding principles here? What are we really going after, right? So first and foremost, we talked about the OFI lib fabric layer and its advantages. And in this case, the hardware adapter itself will be designed around that OFI lib fabric interface and being the most optimized implementation for it possible. So you'll get improved performance and acceleration on the next generation of hardware for anything going through that OFI layer. We'll move to support additional topologies that are low diameter. These would be things like Dragonfly, Megafly, HyperX, in addition to continuing to support the tree topologies that we support today. That's particularly important for certain sizes of deployments. You get to very large deployments, and there can be significant cost savings by moving to the more advanced topologies than a tree. But we fully expect most of the smaller clusters will still remain in the tree environment where performance and cost tends to be near optimal. The focus will also be on maintaining the low latency, but doing so at any utilization and scale. And so what that really means is doing a better job of adapting to different traffic conditions and controlling, trying to avoid congestion, things like that. And the goal is there to make that, the tail latency as small as possible, because that tends to be what is the limiting factor on tightly coupled compute jobs, right? And we go about that in several ways. We have some very advanced adaptive routing that will be added in. We'll have more awareness in general in the fabric in terms of telemetry that is available and utilized to make decisions, right? Tie that in with some of the capabilities associated with dynamic virtual fabrics that can be used for multi-tenant security and various levels of quality of service. And you end up with a very flexible control scheme that allows you to dynamically deal with a lot of different fabric conditions very effectively, and ensure that regardless of how heavily loaded the fabric is, the most important messages get to where they need to go as quickly as absolutely possible. And so this is the general idea moving forward with Omni-Path. As we move forward from 400 into 800, we'll build on that even further. So the idea is to make the interconnect itself more and more intelligent in how it manages itself and how it deals with its traffic. And with that, I'd like to pass it over to Russ to talk to you about success with Cornelis.
Thanks, Glenn. So as we come to the end or towards the end of the presentation, you've heard a whole bunch of things about the heritage and the ancestry of where this all came from. What's important to you guys when you deploy these products and you roll them out there is performance, making sure that your product and your solution delivers you the best solutions. Glenn has done a really good job of explaining what's coming out with OPX. We've focused a lot on latency and some of those type of synthetic type of benchmarks, but what really matters to you is going to be real world performance. And we absolutely do have real world performance. We have a number of years of deployments with this type of technology to show you top 500 deployments. We have benchmarks, and we have documents out there that we can show you how we compare CFD codes and things like that. We do tremendously well. We also scale quite well as well. What we didn't show, I guess we showed a little bit of it, is the more you scale, the more that you will see the advantages of the Omni-Path technology. And why is this? This is because if we go back to what Brandon said, it's that heritage of where we come from. It's $1 billion of investment of technology, of development, and intellectual property. It isn't just the PathScale and Silverstorm, and then QLogic coming out with what was an InfiniBand product at that time. It's not just that acquisition turning into OPA. It is the Cray ASIC technology. You guys may remember the Aries deployments out there. That's where the sort of the way we handle the packets that Glenn was talking about. So as you roll out an application, it's not just that there's a latency, how we handle the errors, how we send those messages, all the things that we do come from $1 billion of investment that deliver today an industry-leading application performing fabric that we deliver to the market. And it's really important to understand that we're now taking that platform with the new software stack, and we're giving even better performance, and then we're going to be delivering you 400 in the next year. So this is a proven product that's been out there for a while, or technology that's built on years of product IP and technology. So the name Cornelis may be new to you, but names like Omni-Path and QLogic and the QDR and InfiniBand and the stuff that rolls into this, the Cray Aries stuff, is not new stuff, and it is very reliable. It is proven technology. So first, I want to make sure you understand that we've got great product and great technology. The next thing is that you're going to want to know that it can scale, which we also have discussed today. So it's not just a product that 2 nodes at scale. The more you scale this product, the more you scale your workload, the better your solution is going to look, the faster we're going to be, and actually the better we do against the competitive products in the marketplace today. We also have a price advantage. We have incredibly competitive pricing on our products today. You'll be even more impressed, and we can talk to you in the future and under NDA of where we're going to be with the 400 product and decisions we've made that are going to make our ongoing products very competitive. And you're not going to pay, as you go to the next generation products, these big uplifts in costs for maybe short-term smaller increases as the applications and the performance of the CPUs drive more bandwidth. We do quite well with that today. So we give you the performance, we give you the scalability, we give you the pricing, and as a result, we're showing to you here, how do we compete today at a price comparison? And we compare quite well. And what's interesting is, and you'll see in the next slide, if you look on the right, there's an example of a dual rail versus HDR 200. But very recently in the middle there, we've actually gone back out there. Now that we're back in the market, we're pushing these technologies. We've actually shown and are deploying in many solutions out there today, the fact that we are able to deliver on 100 today, our OPA 100. And there are, like Glenn said, instances where you absolutely will want to go to dual rail and go to 200. But in many instances, we do phenomenally well with 100, and we've outperformed in many, many deployments out there that we're deploying today, the HDR 200 at a fraction of the cost, lower run times at a fraction of the cost. And this is because it's not just about the latency, it's about all those other things that we put into that technology that allow the applications to run properly. So as a result of all of this stuff, we've won some great awards out there. Obviously, we've been in the top 500. Brandon mentioned that before. We did just win a nice HPC Wire Award for top 5 products and technologies to watch. That's inclusive of our next generation product, as well as this new software stack, which is, as you can see from what Glenn showed you, pretty impressive. During all of this, we continue to win. We continue to be selected for solutions. One that we can highlight here that we can discuss today is the CTS2 selection, where we will be deploying the Omni-Path product and future generations of it into everything from about 200 nodes of a cluster up to thousands of nodes, all using this same technology, and through very stringent bake-offs to show excellent performance, and obviously at extremely competitive pricing that we have out there. So we're really excited to be working with you and to be able to deliver a solution out there that is proven, it can scale, it's price effective. And what we also didn't mention is it's available. We've had a lot of work over the last year to work with our supply chain to make sure that we're working ahead of what we are seeing as an issue in the industry. And if you want to deploy today, it's not going to be a 5-month, 6-month, 9-month delay to get our products. In many cases, switches and adapters are available within a week or two a week or two, because we have to box it up. But we have the product ready to ship out today. And in most cases, we have everything you need if you wanted to deploy we're in February. So we're providing you with a list of your contacts at Cornelis Networks. We have a whole team of folks who are here to help you on the call today. Of course, you've got myself, you've got Glenn, and you've got Brandon, but we have a whole team here to support you with your efforts. If you're international, we've included our EMEA and our PRC contacts. We have additional contacts around the world, so please do not hesitate to reach out to us, and we can help you with your individual deployments, the problems that you're running into that we can help you solve, and help you deliver sooner than later at an extremely scalable, performance-friendly, and cost-effective solution. So at this point, I think we're open for questions. Wade, back over to you.
Thank you for that, Russ. We do have a question from one of our guests today. Martin asked the question, what is the advantage of specific communication interconnects like Omni-Path and InfiniBand as compared to single Ethernet fabric running on other things such as Slingshot?
Sure, I'll be happy.
You take one.
Yeah. So, fundamentally, it all comes down to performance requirements for tightly coupled computing. Okay. And this goes back to why InfiniBand came about in the first place, and it continues even today. Originally, Ethernet offered neither the bandwidth nor the latency performance necessary for really tightly run compute jobs. And by moving to InfiniBand in the early days, you were able to cut that latency, and in particular the tail latency, down. And that oftentimes can translate into very significant application performance differences for multi-node MPI style jobs, distributed computing style jobs, which then turns around and translates directly into either more scientific throughput or more ROI for the industry, or whatever your particular application is, right? So at the end of the day, it all came down to economics. Moving forward to today, it's the same sort of thing, right? So Ethernet can provide the bandwidth now that you see in some of these other fabrics, but the latency and message rates are not close, right? So InfiniBand and in particular Omni-Path provide much lower latencies and much higher message rates. And for small messages that are crucially important for a lot of tightly coupled distributed compute type jobs, the difference is absolutely staggering. That also includes oftentimes the way that the fabrics deal with congestion. Ethernet's tail latency, when it runs into problems, it can be extremely long compared to both InfiniBand and in particular Omni-Path. So at the end of the day, the need for moving to a fabric such as InfiniBand or Omni-Path is tied to essentially your application space, right? So the more you're going to use resources computationally in a distributed fashion, communicating across the fabric during the actual compute time, the more you're going to want to move towards Omni-Path over Ethernet. Okay. If you're instead deploying large clusters where essentially all your jobs are going to be single node, maybe it's not quite as important. But the reality is that as we move into this new environment where everything's pushing to the edge and you have more and more compute in all the small devices out there, the need for high performing, low latency type fabrics is actually just going to grow.
Yeah, and Glenn's talking, Glenn, you talked very on the technical side. I would add that again, price is going to be a big advantage as well. In many cases, even 100 gig Ethernet is not an inexpensive solution. So I would have you take a look at what it would do, or what it would take to deploy a solution price-wise with an Omni-Path product, even versus an Ethernet product, where we believe we're going to outperform it, but we're also, I think, going to be highly competitively priced.
Well, sure. And to take that even one more step, Russ, I think it's important when you're doing your cost analysis to take into account the actual returns you'll get when using the cluster, right, as part of the total TCO. If you're able to use, for instance, Omni-Path and end up running, for instance, we had a recent case where some of our CFD work was running 13, 14, 15% faster than a competitor interconnect that cost over twice as much. Well, that's 13% more product for the same amount of operational cost.
Right.
And when you start doing TCO analysis, that adds up really quickly over the lifetime of the cluster. So I think it's very important that cost is considered, and that not just the deployment cost, but the cost over the lifetime of the system and what you can get out of it from an ROI perspective.
Yeah, and in the current environment, if you're looking to deploy in the next 2-3 months, I've always been, Stephen Wheat was a big proponent, if you know him, of area under the curve. How quickly can you get that compute out there, and how much over amount of time can you get compute done? And one example is a customer who needed to deploy in December. He could not deploy with alternative solutions until June or after, and they are already deploying the solutions today because we can deliver it. So all three are reasons. The third one is more of a situational advantage, but that's another advantage of the current solution versus some of the other solutions. Hopefully, Martin, that answered your question.
I believe that concludes the questions that we have for today. Brandon, Glenn, and Russ, I want to thank you for joining us and presenting this to us today. And for anyone who has questions about how this could integrate with an advanced clustering system, we'd be happy to talk with you about that. This recording will be made available on our website, advancedclustering.com, within the next few days, and it'll be available in our webinar section. You can also join us for previously recorded webinars about how we build clusters, and we also have a recent webinar about our cluster management software, which we can share as well. I want to thank everyone for joining us today, and have a great day.